Hey everyone, my name is Gavin, and my project was on electron dynamics and amplification in a relativistic magnetized Ubitron. I primarily worked with Dr. Sprengel. So, an overview of my project. The goal of this research was to study the dynamics in the relativistic magnetized Ubitron. We call it an RMU. The RMU is a device for generating coherent radiation from the microwave to the X-ray regime. The RMU consists of a relativistic electron beam propagating in a periodic magnetic field and a longitudinal magnetic field. We obtained expressions for the magnetic fields of the RMU, as well as expressions for the self-magnetic and electric fields of the beam. We derived the equations of motion for the relativistic electron beam, and using those we got a stability condition on the orbits, which are verified through simulations in Mathematica. We derived the dispersion relation for the amplification of the input signal and obtained expressions for the growth rate of the input signal. And finally, we found parameters for a 1.5 gigahertz radiation source, and we simulated those in Mathematica. So the way that the RMU is set up is shown in this schematic here. So there's a relativistic electron beam injected into the spatially periodic transverse magnetic field. We call this a Wigler field. It oscillates uniformly in the X and the Y directions and propagates along the Z direction. We also had a uniform longitudinal magnetic field, this B0, which points in the negative Z direction. So in this device, we input the input signal, which is the microwave radiation, and it propagates through here. This is the equation for the Wigler field. And we have lambda W is the period of the Wigler field, with Kw being the wave number. We used the relativistic Lorentz force equations to derive the electron orbits, as shown here, with this d gamma dt proportional to v dot E, where gamma is just the relativistic mass constant. The radiation field and the cell fields are given by the following expressions. We have the radiation field here, which is a wave propagating in the Z direction with frequency omega and wave number k. We use Maxwell's equation here, Faraday's law, to derive the magnetic field of the radiation. And then we use Maxwell's equations to find the E self and B self fields of the electron beam. So we then came up with the equilibrium trajectories, neglecting self fields. And so Vx0 and Vy0 are just proportional to this Vperp that we created. And Vperp is basically reliant on this cyclotron frequency of the Wigler field given here. And it has a resonance where the relativistic cyclotron frequency of the longitudinal field is equal to this k wiggle times Vz0, which is the period of these oscillations. We use these equations to derive a stability condition given by this inequality. And so when this is satisfied, then the beam will be stable, and when it is not satisfied, then the beam becomes highly unstable and falls apart. We came up with the equations of motion, including self fields, and they are a series of differential equations that had no apparent analytical solution, and we simulated these using Mathematica numerically. As an example of these simulations, we have two phase space diagrams. This is the phase space in X. So this diagram on the left is when the stability condition is satisfied. So as you can see, the orbit comes out to this stable point and just oscillates around. While when the stability condition is not satisfied, it is highly unstable and does not follow any sort of periodic motion. So we came up with parameters for prototype design for an approximately 1.5 gigahertz RMU. And this just happens to be the frequency of GPS signals. And so the parameters for that are a beam energy of approximately 1 MeV, which leads to an initial gamma factor of 3, beam current of 3 kiloamps, and a beam radius of 6 millimeters. The axial magnetic field is approximately 300 Gauss. The Wigler field amplitude is approximately 1 kilogauss, and the Wigler period is about 3 centimeters. So then we went on to find a dispersion relation for the wave. So we use this one-dimensional wave equation given by JR. JR is the driving current of the electromagnetic wave, and this JR is then proportional to the amplitude of the radiation wave. So to simplify the algebra, we took B0 to equal 0, and we were able to verify the dispersion relation in the case for the free electron laser and the high gain limit, which this is the resonance of the free electron laser given here, And when we solve this problem in a vacuum, K becomes omega over C. And we solve for omega, we can find that omega equals this expression here, where we have this 1 minus BZ0, which shows that omega can get quite large as the energy of the beam is increased, which can lead to coherent radiation in the X-ray regime, which is quite special. And this 1 minus BZ0, which is represented here as this gamma squared Z0, shows a Doppler shift, or 2 Doppler shifts really, of the frequency, which is how it gets so large. So using this wave equation, we derive the dispersion relation between the EM wave and the beam mode. So this here is the dispersion relation, which relates this omega to this CK here. And so it shows in this expression where we have defined omega, we are relating the EM field to the beam mode here by this delta omega. Solving for this delta omega, we get this expression here, which has 3 unstable roots as it's a cubic function. And one of those roots leads to a amplification of the system at that frequency. And we have this proportional to this plasma frequency squared defined here. So in conclusion, we came up with the equations of motion of a relativistic electrons, including self-fields and the RMU, and derived a definition of the stability condition. So the stability condition was numerically simulated and validated. We came up with a dispersion relation that showed the coupling between the EM fields, which are the microwaves in this case, and the various beam modes. And the dispersion relation for B0 equals 0 for the electron laser, and the high gain regime was derived. And then we designed parameters for a frequency of approximately 1.5 gigahertz radiation source, and we obtained that and simulated it. We plan to continue this project in the highly relativistic regime with the goal of producing a publication. Thank you for your time.